Hello and welcome. In today's lesson, we are going to look at trigonometry. Specifically, we are going to look at the sine and then the cosine rules. In our last video, we looked at how to solve problems concerning right-angled triangles. That is, we looked at how to find the sizes and angles of right-angled triangles. And we said that in order to find the sizes and angles of right-angled triangles, we could use what we call the Pythagoras theorem. And we could also use the three trigonometric ratios in order to relate the sizes and the angles. Now let's look at a case where we have a triangle which is not right angle triangle. In order to find the sizes and angles of triangles which are not right angle triangle, in other words, we cannot apply Pythagoras theorem. That is, if none of the angles of that particular triangle is 90 degrees, we cannot apply Pythagoras theorem. So, when a triangle is not a right angle triangle, how can we then find the sizes and the angles of that particular triangle? Let's consider the triangle below. Triangle ABC is not a right angled triangle. That is, none of the three angles is equal to 90 degrees. But let's consider the sizes labeled as ABC. That is, side AC is labeled as B, small letter b. Side BC is labeled as small letter A, and that of AB is labeled with small letter C. Let's say that there is a perpendicular line from C to meet at AB at P. This perpendicular line, or the vertical line, has an angle of 90 degrees on both sides on line AB, as indicated in the diagram below here. So when we have this, from triangle ACP, sine of A should be equal to the magnitude of CP over the magnitude of AC, where we know that AC magnitude is the same as B. So sine of A will now be equal to magnitude of CP over B, small letter b. We can also say that, which implies magnitude of CP will be equal to B sine of A. We can also say that from triangle BCP, sine of B should be equal to magnitude of CP over magnitude of BC. Sine of B should then be equal to magnitude of CP over small letter a, since magnitude of BC here is equal to a. So this implies that CP magnitude will be equal to A sine of B. So when we look at that, CP here is equal to A sine of B. Again, CP here is equal to B sine of A. That means we can equate the right hand side of the two equations here. Since the left hand sides are equal, that gives us A sine of B, that is this, equal to B sine of A, which is here. Now, when we are to group them, let's say that we are going to group A with sine of A, B with sine of B. If we are to do that, we can leave the A here and divide through this one by sine of A, which is equal to B here. Then we'll have sine of B here. So this then gives us A over sine A equal to B over sine of B. Or here we could have said that let's divide both sides of the equation by sine of A and sine of B. So that when we do that, the sine of B here would have cancelled the sine of B down there, leaving sine of A. Then on top here you have your A. That will give us that equal to this one to one. We divide by sine A sine B. Sine A will cancel sine A, leaving sine of B, which we have here, and the top will also be left with B. That gives us A over sine A equal to B over sine of B. And this is what we call the sine rule. Let's consider the triangle here, which we already showed previously. When a triangle is not a right angle triangle, as we indicated above, we can also say that from triangle ACP, this particular triangle, which is already a right angled triangle, when we consider that, we can now say that the hypotenuse squared is equal to the sum of squares of the other two sides, that is this side and that side. So when we are going to relate that using the Pythagoras theorem, we'll have AC squared, magnitude of AC squared, to be equal to magnitude of AP squared plus magnitude of CP squared. But in this case, we know that AC magnitude is represented by B. So this will now give us B squared equal AP squared plus CP squared. When we look at the triangle here, AB magnitude is represented by C. Okay. Or AB magnitude consists of AP magnitude and BP magnitude. So I can say that AP magnitude is equal to AB magnitude minus BP magnitude. Now have our plus magnitude of C squared. Let's consider from triangle BCP, we can say that cos of B of this particular angle will be equal to the adjacent, which is BP magnitude, over the hypotenuse, which is BC magnitude. But we know that the hypotenuse is A, small letter A. So cos of B will be equal to BP magnitude over A. Let's cross multiply. This gives us BP magnitude to be equal to A cos of B. That is from triangle BCP. And already we established that magnitude of CP is equal to A sine of B. So anywhere we now see magnitude of BP, we are going to change it to A cos of B. And when we see magnitude of CP, we are going to change it to A sine of B. So replacing them here, the BP here will change to A cos of B. Then the CP here will also change to A sine of B, whilst the AB here changes to this, the C. So let's do that and see what we are going to get. So when we do that, we'll now have B squared equal C minus A cos of B squared plus A sine of B squared. Let's expand this and that. So expanding them, we'll have B squared to be equal to A squared C squared minus, when we square this, we have C squared. Then multiply this by that, we'll have AC cos B. Again, this by that, we'll have AC cos B minus. Then when we square this one, we'll have plus A squared cos squared of B. That is what we'll have here. Then plus this one square will be A squared plus A squared sine squared B. So when we group them, we'll now have B squared to be equal to A squared cos squared B plus A squared sine squared B plus C squared minus 2AC cos of B. We have grouped them. So this one, the C squared comes here. The A squared cos squared B comes here. Then we have A squared sine squared B here, gives us that. Then minus this and that combines to give us this. So when we now have this, to simplify that, we can see that we have common terms here. A squared, A squared. Let's factorize A squared out. So that we'll now have B squared to be equal to A squared out, cos squared B plus sine squared B plus C squared minus 2AC cos B. After that, we also established in our previous video that cos squared B plus sine squared B is the same as sine squared B plus cos squared B equal 1, which is equal to 1. So in place of cos squared B plus sine squared B, we are going to change it to 1. So this will now be A squared by 1. That gives us A squared. Plus C squared, this, minus 2A C cos B. So we'll now have B squared to be equal to A squared plus C squared minus 2AC cos B. And this is what we call the cosine rule. Let's now look at examples related to the cosine rule and then the sine rule. In the example 1, if we are asked to find in the diagram below the magnitude of AC and the value of the angle represented by theta. Let's see how we are going to solve that. For the I, in order to find the magnitude of AC, we can use the cosine rule since the triangle is not a right angled triangle. So using the cosine rule, we are going to consider the side which faces the angle at B. And in this case, the side facing the angle B here is AC. So AC in this case becomes our leading side. So that gives us magnitude of AC squared to be equal to AB squared plus BC squared. That is the sum of squares of the other two sides. But because this is not a right angled triangle, we'll have minus 2 multiplied by the product of the other two sides. So you can see that we have AB magnitude, we'll have here BC magnitude. Then cos of the angle at B, the angle facing AC. So that will be 135 degrees. But in this case, we are given the value of AB, we are given the value of BC. So let's substitute them. Substituting AC magnitude squared should be equal to 5 squared plus 8 squared minus 2 multiplied by 5 by 8 cos of 135 degrees. So simplifying, AC magnitude squared should be equal to 25 plus 64 minus 2 by 5 by 8 gives us 80. Then we'll have 80 cos of 135 degrees. 25 plus 64 minus 80 cos of 135 degrees. We'll simplify everything. That gives us 145.57. AC squared magnitude squared will now be equal to 145.57. In order to find AC magnitude, we will take square root of both sides, and that will now be equal to square root of 145, square root of both sides rather. Then that will now give us AC magnitude to be equal to 145.57 square root of that, which is equal to 12.1. So the magnitude of AC is 12.1 to 1 decimal place. Then for the Roman number 2, we have to use the sine rule. Since we know the magnitude of BC, we also know the angle at B. We also now know the value of AC. So we are going to replace them or relate the two here. So from the cosine rule, we'll have magnitude of BC over sine of the angle facing the BC, which is theta, equal to the magnitude of AC over sine of the angle facing AC, which is the angle at B here, which is 135 degrees. But we know AC, we know BC. Let's replace them and see. So replacing them, we'll now have 8 over sine theta equal 12.1 over sine of 135 degrees. When we cross multiply, 12.1 sine of theta should be equal to 8 sine of 135 degrees. So sine theta will now be equal to 8 sine 135 degrees over 12.1, which implies that sine of theta will be equal to, when we simplify the right hand side, we get 0.46751 to 5 decimal places. Finding sine inverse of the right hand side, theta will be equal to 27.9 degrees. So in the first example here, the value of theta is equal to 27.9 degrees, and the value of AC, line AC, is 12.1 to 1 decimal place. Let's look at example 2. If you are asked to find the magnitude of xz and the angle xzy in this particular triangle. In order to find the magnitude of xz here, we are to use the cosine rule, where xz here becomes our leading side and the angle facing xz is 120 degrees. So the cosine rule will be xz squared equal to xy squared plus yz squared minus 2 multiplied by xy and xz, cos of the angle here, which is 120 degrees. So we know xy, we also know xyz, so we are substituting into the equation. This will now be equal to magnitude of xz squared, giving us 16 plus 9 minus 24 cos of 120 degrees, and magnitude of xz squared should be equal to 37. When we take square root of both sides in order to find the value of the xz, that will then be equal to 6.1. Magnitude of xz will now be equal to 6.1. And to find angle xzy, we use the sine rule. But first of all, let's let the angle xzy be equal to theta. We are looking for the angle at z. So if we are doing that, if we do that, then let's relate two angles in two sides by using the sine rule. We will now say that magnitude of xy should be equal to, over sine of theta should be equal to magnitude of xz over sine of the 120 degrees, where we know that xy is 4, then the angle facing xy is the angle at z. The angle facing the side xy is the angle at z, so which we said it should be theta. So 4 over sine of theta should be equal to 6.1 over sine of 120 degrees. 6.1 over sine of theta should now be equal to 4 sine of 120 degrees when we cross multiply. So sine of theta will be equal to 4 sine of 120 degrees over 6.1. When we simplify the right hand side, sine of theta will be equal to 0.56789, which gives us theta to be equal to sine inverse of 0.56789, and this will be equal to 34.6 degrees to 1 decimal place. I hope you have enjoyed the lesson. Thank you for watching, and please share, comment, like, and don't forget to subscribe to my channel for more interesting and enjoyable videos. Thank you, and bye for now.